On a clear, dark night, you can see thousands of stars in the sky. Some look brighter than others. Some stars look red, while others look blue. The colors of the stars can tell us a lot about them, like how hot they are. Telescopes magnify and resolve objects in space to help us see more detail. Through a telescope, we can see the rings of Saturn, the cloud bands and storms on Jupiter, the polar ice caps on Mars. We can even study the sun and other stars, or faraway nebula regions. But what we see with our eyes is only part of the story. The visible part of the spectrum, what we perceive as color, is only a small part of a much larger range of light waves. The electromagnetic spectrum includes radio waves, microwaves, infrared, ultraviolet, X-ray, and gamma rays. All these can be used to observe objects in space. In the photo are just a few examples of the observatories that are used by astronomers to study these objects. First, let's go to Chile to the ALMA radio telescope. ALMA is an array of radio telescopes that study cosmic light straddling the boundary between radio and infrared. It is the most complex astronomical observatory ever built on Earth. It's opened a window into the universe, capturing never-before-seen details about the very first stars and galaxies. Here's an image from ALMA of a star-forming region with a massive binary system. The background image shows dusty streams of gas that appear to be flowing toward the center of the system. The inset image shows a zoomed-in view of the massive system with the brighter primary protostar moving toward us in blue, and the fainter secondary protostar moving away from us in red. The Earth's atmosphere blocks much of the light in the microwave band, so astronomers use satellite-based telescopes to observe cosmic microwaves. The entire sky is a source of microwaves in every direction, most often referred to as the cosmic microwave background. These microwaves are the remnant of the Big Bang. The first precise measurement of microwave background was done by the Cosmic Background Explorer, or COBE. COBE was launched in 1989. It compares the spectrum of cosmic microwave background radiation with a precise black body and searches for cosmic infrared background radiation. The WMAP and ESA Planck missions continue the legacy of COBE, studying the cosmic microwave background in ever great detail. In 2013, world-renowned cosmologist Stephen Hawking said that WMAP's evidence for the inflationary universe was the most exciting development in physics during his career. Now we go to Mauna Kea, Hawaii, home to the largest optical and infrared telescopes in the world. Because it is near the equator, Mauna Kea makes an excellent astronomical observation site. But even the best telescopes on Earth have significant limitations. They are hampered by the distortion of water vapor in the lower atmosphere that blocks most infrared, ultraviolet, and all X-ray and gamma rays. SOFIA is a Boeing 747 modified to carry a 2.7 meter reflecting telescope above 99% of Earth's infrared blocking atmosphere. Spitzer, James Webb, and Hubble are a few examples of telescopes that are in orbit around Earth right now. Each telescope is equipped to perform at specific wavelengths. Hubble observes in the infrared, visible, and ultraviolet. James Webb is optimized for near to mid-infrared, and Spitzer observes in the far infrared. Using a combination of wavelengths allows astronomers to observe more about galaxies, stars, and planets. Here we see features of Jupiter in infrared, visible, and ultraviolet light. One of the main features is the Great Red Spot, which is a very long-lived storm in Jupiter's atmosphere. Notice it's almost invisible in the infrared image, but shows up clearly in the ultraviolet and visible images. NuSTAR is a high-energy X-ray telescope designed to study supermassive black holes at the cores of galaxies and probe the creation of heavy elements in the cataclysmic death throes of massive stars. Chandra helps astronomers study the history and evolution of the universe. Observations are made of high-energy regions such as supernova remnants, X-ray pulsars, black holes, neutron stars, and hot galactic clusters. ZWIFT is a three-telescope space observatory that studies gamma ray bursts and monitors the afterglow in X-ray, UV, and visible light. Fermi is a telescope that scans the entire sky every 3 hours. The instruments on board enables scientists to study supermassive black hole systems, pulsars, and the origin of cosmic rays. This animation shows gamma ray activity during a year of observations. Each magenta circle represents a gamma ray source growing as it brightens and shrinking as it dims. Over 90% of these sources are a type of galaxy powered by the activity of a supermassive black hole. The yellow circle represents the sun following its path across the sky. The reddish-orange band running across the middle is the central plane of our Milky Way galaxy, which is a consistent gamma ray producer. Here is a graph analyzing the light from stars showing the intensity and wavelengths for objects at 4 different temperatures. First, notice the curves show that at each temperature, radiation is emitted at all wavelengths, so we find a broad range or spectrum of energy. Second, note that an object at higher temperature emits more power at all wavelengths than does a cooler one. This means that the hotter star gives off more energy than cooler stars. Third, the graph shows us that the higher the temperature, the shorter the wavelength which the maximum power is emitted. It makes sense then that hot objects give off a larger fraction of their energy at shorter wavelengths than cool objects. We use these ideas to come up with a rough sort of thermometer for measuring the temperatures of stars. Because many stars give off most of their energy in visible light, the color of light that dominates a star's appearance is a rough indicator of its temperature. One star might look red while another looks blue, and since blue light is a shorter wavelength color, it is the hotter star. We can develop a more precise star thermometer by measuring how much energy a star gives off at each wavelength. The location of the peak in the power curve of each star can tell us its temperature. The average temperature at the surface of the Sun is 5,800 Kelvin. The wavelength at which maximum power is emitted from the Sun can be calculated using the formula. T is a temperature in Kelvin. So by substituting in 5,800 Kelvin, we find that the wavelength max is equal to 520 nanometers. 520 nanometers is near the middle of the visible light portion of the electromagnetic spectrum, so our sun emits a greenish light, but our eyes have evolved to perceive it as white. We can describe our observations that hotter objects radiate more power at all wavelengths in a mathematical form. What we usually measure from a large object like a star is the energy flux, the power that's emitted per square meter. This can be written in the form of an equation where F stands for the energy flux. And then we have a Stefan-Boltzmann constant, and T is the temperature in Kelvin. By substituting in the value of the constant and the temperature of the star, our sun, we calculate the energy flux to equal 64 million watts per meter squared. While energy flux tells us how much power a star emits per square meter, we would often like to know how much total power is emitted by the star. We can determine that by multiplying the energy flux by the number of square meters of the surface of the star. Stars are mostly spherical, so we can use the formula 4 pi r squared for the surface area, where r is the radius. The total power emitted by the star can be found by multiplying the formula for the surface area of the sun by the energy flux we calculated in the previous step. Substituting in the values, we get that the power is equal to 3.9 times 10 to the 26 watts. Now compare that to your average light bulb, which puts out about 60 watts of power. It's no wonder our sun is so bright, even though it's 93 million miles away.